Basically page views and page views only at that time. Currently, we do about 2.5 billion dynamic HTTP requests per month. That includes page views, internal APIs, external APIs, global APIs, all that kind of stuff. We're one of the top 5 social networks in the United States. According to HitWise, we're the #1 teen destination on the web, according to ComScore. And we're one of the top 25 most trafficked sites in the United States, according to ComScore as well. And we have 99% uptime. Now, you're probably saying, my yearbook, who's that, right? You're not our target demographic. I'm not the target demographic. But basically what we are is a social network that is focused on friend discovery. So unlike Facebook and others in the area that are focused on your own social graph, my yearbook is all about making new friends on the internet. We focus very heavily on introduction based upon geolocation and proximity. So when I started in 2007, it was basically, we were in a managed data center. We had one Postgres server, one web server running Apache and PHP, and a couple static content servers that were serving up user content, profile photos, that sort of thing. And I would get one phone call a night that the site is down because of something going on, usually related to Postgres. Poorly configured, the application wasn't written in a way to make best use of the database for indexing, that sort of thing. For 2010, we're in 2 data centers. We have 16 message brokers, a combination of ActiveMQ and RabbitMQ, 35 Postgres servers, 100 memcached servers with 1.2 terabytes of active cache. We actually have more available than that. We have about 100 miscellaneous servers that fill everything from email to queue consumers, monitoring, deployment, that sort of thing, and roughly 400 web servers. This floats on a day-to-day basis as machines fail. We reuse machines on newer hardware, that sort of thing. There's a lot of buzzwords or keywords up here, or key architecture components. We're primarily a PHP shop, but we've been moving more and more to Python for our heavy asynchronous I/O related needs. We use Apache HTTP primarily. We've been using Cherokee, which is in the same vein as Nginx. If you're not familiar with it, I would go check it out. It's like Nginx, but better documented and easier to work with. We use LineHTTP for image serving for our content-related stuff. We have Slid sitting in front of that. We use F5 big IPs, multiple of those as our front-end load balancers. Postgres is our primary database. You can catch that by now. Lots and lots of memcache. Our message brokers, we started with Apache ActiveMQ. We're moving to RabbitMQ. We use Tornado on the Python side for our web development aspect. And on our shared disk, we use XLNAS. Message systems, Momentum for our email delivery. And we're in the middle of migrating from Subversion to Git. So the very first thing that I learned at my yearbook over the course of 2007 was growth is a double-edged sword. It's really great to have a popular site. It's really great to have traffic that's going through the roof. But at the same time, it's painful if you didn't plan on it up front. It's painful when you haven't learned the lessons that you have to learn to be able to accommodate the growth, to accommodate server load, and that sort of thing. So through that experience, I basically came across this concept of a growth cycle for internet startups. You prototype, right? Product development is very key in early stages in a startup. What is our product? What are we going to do? We launch that. We fix problems because we didn't think of every edge case. We didn't think of everything that we needed to think about from a scaling perspective. We add new functionality. Product dev is always pushing. New. Keep the users engaged. Keep them active. And we repeat steps 3 and 4. And that's pretty much the cycle. What happens is in step 1 and 2, you generally have a very limited budget. You also have very limited time and resources. Right? You have to get the product out quickly. And you have to do it in the most optimal way, cost-wise. Steps 3 and 4, as an organization matures, your budget increases. You may be able to buy the neat toys. You don't have to buy the cheap Sun J-Bot that's going to have the firmware issues. But you still have limited time and resources. There's only so much time in the day, and no matter how quickly you can staff up, there's still not enough to meet the demands of a fast-growing web development shop. And so you plan and plan and plan. You think of all the contingencies that you can think of, but things never go exactly as you want them to go. Whether it's bringing on a new box, putting in a new switch, writing a new application, deploying it, refactoring code, there's always something that's going to grab you. You can't think of every single case, every single edge case. And so you're always figuring stuff out. Hopefully you retain that as things go on. And so the best way to retain that is to instrument your application, instrument your infrastructure. Do it early. Start at the beginning. Think about how you're going to keep key metrics about your application right up front. And make sure you do it at a pretty deep level. How much time is it taking for me to go out to memcache and get that data and bring it back? Because one day, when you're trying to troubleshoot an issue and the site's running slow and you can't figure out why, what's the best way then to go and look at the individual components of your application and figure out where that latency is coming from? So you need to know your systems, and you need to know them deeply. You need to know your key application metrics. Whether you're using memcache and you want to know about the number of items that are in your memcache, what your hit ratio is, your network throughput. We go all the way to our APCs and power distribution units and figure out how many amps are we using on a per PDU level and everything in between. As a matter of fact, currently when you're looking, we have 238 categories of metrics that we collect. That's applications and systems and that sort of thing. And in those 238 categories, we have 5,558 individual items. And those items can have 1 metric or 25 metrics. I think some go up even bigger than that. So an item might be a Postgres server. And in that Postgres server, what do my logs look like? And then break down the different type of logs. We'll get into that a little bit later. So what we use for gathering analytics, we have an in-house tool called Stapler. We're getting ready to release version 2 of Stapler, which is a complete engineering design. We have a tool called Posuda for Postgres. It collects internal data about Postgres, logs it, gives us a nice interface to figure out what's going on. We use Nagios for alerting. We use Cacti in various areas as well. And then there's the traditional third-party external Google Analytics for page views and uniques and all that kind of fun stuff. But also availability and performance. I noticed some Pingdom charts up on the screen yesterday. We use Pingdom, we use Alertra, we use Gomez. We're probably close to adding Keynote. We believe in getting as much information from as many different parties as we can that tell us about what we're doing so that we can look for problems before they become major problems. So, scaling databases. It's kind of a key thing in talking about the generic web scale, which I really hate. I hate the term web scale because web scale means different things to different people. And my version of web scale in my yearbook is completely different than Facebook's version of web scale, right? But it's probably pretty close to Etsy's version of web scale. Traffic is roughly similar. Pretty close to, from a page view perspective, to Apple, for example. So scaling databases is often talked about. You have NoSQL now, which is poorly named in my opinion. You have MySQL, you have Postgres, you have Oracle, right? But the concepts are generally the same. You want to plan for growth when you're writing your database. When you're putting your database systems together, CPU, get the best CPU you can based upon what your needs are. Most databases are never CPU constrained. As a matter of fact, most databases at scale are IO constrained. And so you want to get your disk based upon need. And I say need is not just capacity, but throughput. And you want RAM based upon budget. You buy as much RAM as you can, and then you buy 2 of those machines. And for every machine you need, you buy 2. And that's because hardware fails. And we want all of us want our uptime at 99.99. And if you have one database machine and your LSI controller goes bad, right? That machine goes down and you need a way to recover quickly. And you can't do that unless you have this spare failover machine. Or if you work in a clustered environment where things scale out, but even in that environment, you want to have access to that data. So unless you have some sort of RAID type protection of your data across multiple nodes of your database, you do still need that failover. So there are multiple ways to scale databases, right? You can scale up. You can buy bigger, faster hardware. Postgres works really good with that. Currently, our biggest box is a 48-core, half a terabyte RAM box. Works really good. It's smoking. It beats the pants off the 32-core, 256 gig box we had before. You get better, faster software. In the Postgres world, that's great because every major version of Postgres that comes out addresses performance in some way or another. So version 9 is faster than 8.4. 8.4 was faster than 8.3, et cetera, et cetera. And that's one of the great things that I like about the Postgres community because they're always looking at how to make it better, not just how do we add features for feature's sake. You can scale out. Everybody knows about sharding, right? You take the data and you spread it across multiple nodes based upon the CRC of a hash of the value, and you know that user 1 is on database 1, and user 2 is on database 5, et cetera, et cetera, et cetera, as you spread across your hash. Another way that we do it is we use server-specific databases, or service-specific databases. I should explain what I mean by that. We basically have taken this service-oriented approach of saying, this application is going to live on its own hardware and its own silo. We don't necessarily follow a very strict model of that. There are interdependencies, but for the most part, the windy application on my lives in its own database. It's got its own web servers, its own memcached servers, its own message brokers, that sort of thing. And for Postgres-specific scaling, there are some important things that we learned. Anecdotally, we had an HP 585 G2, and it was an 8-core machine. It was like 32 gigs of RAM at the time, and that's what I inherited. So I decided I was going to go out and find the biggest in the x86 market machine that I could get, and I ended up at Sun. And I bought a Sunfire X4600. And it was a cool box. It was 16 cores, probably 64 gigs of RAM at the time, and we threw Postgres on it. And it was a dog. And we had at the time, let's say, 10 web servers running against it. We couldn't figure out what was going on. But one of the things that's key about Postgres is the more connections you have to it, the more work it has to do because it has to share log state information across backends for those connections. It's a process port model. So it's using shared memory for every Postgres backend and saying, hey, I've got this table logged over here, so you know, connection number 20 can't use it. Well, when you scale it up and you've got 1,000 connections, or 2,000 connections, or 5,000 connections, it becomes even more problematic. Java addresses this by having built-in connection pooling, but we were in the PHP world. And so I'm on the phone with a friend of mine, and I'm saying, hey, you know, what's going on? We have to work at Sun at the time. He's also very active in the Postgres community. I'm like, you know, help me out here. And he's like, well, are you connection pooling? And I said, connection pooling? What do I have to worry about that for? Right? But it was key. As soon as we threw a connection pool in front of what was going on, the performance increased dramatically. The slowdowns that we experienced went away. So we used PG Bouncer. It was developed by Skype. It's a part of a suite of tools that Skype uses to scale out their Postgres installs. Big fans. It works very well. There's also PG Pool, or I think at this point it's PG Pool 2. And all basically work on the same principle. Let me be a proxy in the middle that handles all of those connections and pass through queries using the small set of backends that I can. PL proxy is another tool that was developed at Skype that we use for scaling horizontally, for sharding. For example, our messages system is sharded across 8 boxes, and messages for a particular user go to one particular box, and for another go to another. What's unique about PL proxy is the way that it works is it's a procedural language, so functions are defined that you might say, get my messages, and passing my member ID. PL proxy then says, let me go look at my configuration data, let me hash that, and figure out what box that sits on. And then it runs a same named function on the other end. It adds a really nice layer of transparency to how you write your applications, because you write your core function that does what you need it to do, and then you slap PL proxy in front of it, and it scales out. Read-only nodes, for heavy read environments, searching, that sort of thing. Lumbistic, Splony, Bucardo, key replication technologies for generally single master, single slave, or multi-slave nodes for that readout. Postgres 9 adds hot standby, so you can actually query a standby server, and so it makes for a good read-only node solution as well. Table partitioning, key to scaling Postgres when you have large volumes of data, especially in our case where we have large volumes of data that we want to get rid of on a regular basis. Part of the way that the Postgres data model works is it uses MVCC, it versions the rows, and if you go through and you delete the row, it leaves a dead space in the table where that row used to exist. And so you basically have to go through and reclaim that. That's true of indexes, it's true of tables, all relations within Postgres. The vacuum, as you may have heard, with Postgres. And as Postgres has grown, there have been more and more strategies on how to deal with this effectively to make it less impacting overall. But the most effective way that we've done, where our data is transient, it gets on the database for 7 days, it gets on the database for 30 days, for 6 months, is we partition our data by date. And instead of doing mass deletes, which block the tables, and then we have to reclaim that space, we just drop off the partitions as we no longer need them. And it also allows you to focus your selects on the partition tables if you know that you can use those partition tables, which gives you better performance. Why look at 30 days of data when I can focus myself on one table that has 1 day's worth of data? The other key piece on scaling Postgres, and it's true of any database to be honest, is knowing the internals of what's going on. Postgres has a sophisticated system catalog that is more than just keeping track of the configuration and the data about what tables are there and what indexes are there. It keeps track of statistical data about what's going on in the database. You can see on this chart on the top right, we see heap read, heap hit, index read, index hit. Those are referring to what's going on when you're running queries. And am I having to go through and read the relation itself? Am I having to get it from my own cache? Am I having to read it off the disk? Did I actually go out and hit an index? And was it already primed in Postgres' internal cache, or did I have to go out to disk? These particular pieces are key to performance monitoring, because if I notice that my reads are really high and my hits are really low, and my heap read and my heap hit particularly are disproportionate to my index, I know that there's some tuning I have to do. Locks also, whenever we encounter some sort of major issue where a server goes down, you can almost certainly account it to some sort of lock. And Postgres has multiple types of locks. So knowing if it's an exclusive lock and being held for a long period of time is extremely useful. There's all sorts of data. I try to get a top-level view of this, but Postgres keeps track of many, many internal statistics, and we try to report on as many as we can. And then, anything that can go wrong does. Jack Sack wrote a book on mountaineering in the 50s, and he claims that this Murphy's Law, as we know it right, is an old mountaineering adage. It's really hard to find who really came up with this saying to begin with, but at large-scale operations, as Brian was talking about earlier, when you've got 5,000 disks, you're going to run into problems that you don't have when you have 50 disks, right? And so restoring from server failures is really key at scale, right? If I've got 30 machines, the chances of losing a machine at any given time are much greater than if I've got 1 or 2. Daily backup is not enough. No matter what your database is, restoring that data into the database is an expensive operation. Writes are always more expensive than reads. It's a disaster recovery. It's a worst case scenario. I have no way to get back to where I was. I need this morning's backup. You need to replicate your data over to other nodes. Some databases do this as part of the strategies of the newer NoSQL databases, for example, to spread data across multiple nodes. NoSQL Membase over here in the vendor area, that's one of the key features that their product has. But from a Postgres perspective, we basically use currently worm standby nodes. So for every database server, we have a failover database server that's just sitting there digesting binary log data. And its sole purpose is when something goes wrong on that primary server, and it does, we flip the switch. We basically bring up the standby server as the production server and move on. We use warm standby, which has been in Postgres since 8.2. We will be moving to hot standby as soon as we're confident that 9.0 is exactly what we think it is. Caching is, it's something we talk about a lot in web scale. Memcached is a very, very popular thing. But I wanted to take a step back and look at caching from application performance, covering multiple areas. And so, static content caching. It's key. If you were here for the Wikia presentation, they're using Varnish as a proxy server. Basically, what it's doing is it's taking the cache or the image content, it's caching it in its own resources to deliver it faster. So the way, from a top-down approach that I think of static content caching, images, assets, JavaScript, CSS, is the CDN really is more than just HTTP delivery. At the edge, it's sitting as a cache of all your content. And so basically, the idea of having a CDN node that asks for your image once and then delivers it on multiple requests without going and taking the resources is really key. And then you have an HTTP reverse proxy sitting between there, Squid, Varnish, things of that nature. Those are also caching images. And in that layer, if you're not using it and you're using CDNs, is key. Because what's going to happen is if you have a failure at your CDN, which does happen, you're going to get you're basically going to have a stampede of requests for images and content that you may not be prepared to deal with because you haven't had to deal with that stuff for a while because you've given it to your CDN. Having Squid or Varnish or something else sitting behind the CDN that basically is doing that same level of caching protects your internal resources, your internal disk systems from being swamped by I/O, from accessing images and content that it hasn't had to access for a while. Then you have your web server. One of the things I really like about Cherokee is it has a built-in caching module that is for speeding up delivery of content images. Other servers have the same type of thing. Then you have storage, and if your storage system should support some level of cache as well. And obviously, all the way down to the operating system. The Linux kernel buffer has a lot. Basically, it keeps track of what blocks have been read from the disk, and it keeps the most access cached in memory. And so, when you're thinking about performance, and I'm sure you guys have all heard the statements from Google and Amazon and every other major company that studied this, that the more latency that there is in page delivery time, the higher the abandonment rate. Wikia was talking about that yesterday. Basically, store the performance, the less you can use your site, cache becomes incredibly important in static content delivery to make sure that those assets, that user-generated content is being delivered quickly. Data caching. This is how most people think about caching, at least within application engineering. It reduces your system load, whether it's on your databases or your file system. And at Mayor, we use a tiered approach. So we basically use a in-application execution type of cache where, for example, if we have a configuration file, we're not going to go out to disk every time and say, hey, give us the data from that configuration file for each page execution. We're going to load it in once. We're going to keep that in memory so that if we have to go back and reference that from different objects or different places within the application execution stack, we can. And then at the same time, in an Apache PHP world, even in worlds where you have multiple processes on the same box that are running applications, making use of shared memory. We use specifically APC within PHP to share cache data across backends. That's really key. And then, of course, memcached for keeping track of user data, for example, that's pulled from the database. There are some gotchas in using memcached at scale. It is really, it helps you grow quite a bit, and when you become more and more dependent upon it, it becomes a major source of your network traffic. And I know my NetOps guy couldn't care less about throughput as far megabits per second. He cares about packets per second. It's his primary focus. And memcache is the #1 thing on our network that eats up packets per second. Very, very high throughput. And so looking at the multiple protocols that memcache supports, TCP versus UDP is really important. Binary versus ASCII. Memcache started with a very simplistic ASCII protocol. That's one of the reasons why it's successful as a cache product. It's very easy to use. If I want to go and figure out what's going on, I can run TCP dump. I can go in and tell that to port 11.211 and issue commands and get what I want out of it. But it's not very effective from a client perspective. When my web server is asking for it, it's asking for it a lot. I want to be using binary protocol. It reduces the network footprint of the data that's being transferred and basically makes it quicker. One of the things that we also encountered was because memcache is a single daemon that's designed to be used in aggregate and needs the protocol of how to use it in aggregate up to the client library, different languages have different hashing strategies about where to put data on memcache servers. And different languages also use flags about what that data is differently. And so it's important when you're looking at either changing client implementations or adding different languages into your stack that are going to use memcache, that you're looking at the hashing strategies, you're looking at how data is stored, and making sure that everything is compatible. And then you need to monitor utilization. One of the key metrics on an ongoing basis that we look at for site performance and site engagement is our cache utilization. Because as soon as something is going wrong, whether it's a flapping P2P route, a problem with a firewall somewhere, a problem with an application, we're going to see major shifts in change in our memcache utilization. So monitoring that is an easy early indicator of performance, site availability, and site application performance and that sort of thing. Memcache appliances. I'm sure you guys have seen Schooner, who's out here in the vendor call. They had a competitor near 6. There's a few other people who are working in this space. Basically, it's a pretty young market, and the concept from my perspective, or what I like about them, is it's rack dense cache. And so the idea that I can leverage SSDs for high performance caching of my data that was in memcache previously in a small footprint, 1U box, where I can get, let's say, 256 gigs of cache in one small box in a more cost-effective way than doing it in memory. One of the problems that I have with these, beyond it being an immature market, is that they're really trying to hit as many features as they can to be selling points. Really good for startups, really good for small cache footprints, replication, persistent data storage, fancy UIs. Memcache on its own is very simplistic. It's a day when you start it up, you set the port you listen to, and you're good to go. IP address you're binding to. These, for the most part, you go into a web UI, you allocate the amount of memory that you want for a specific cache pool. You're clicking all these different options in the UI just to get a basic cache instance up and running. So, interesting to look at. I would definitely make sure that you evaluate that as part of your caching strategy. For us, we're going to wait a little bit before we put our toes back into that market. Balance and development practice. From an overall perspective, when you're writing your application, it's hard to think about the scale that your application is going to be. I don't think Mark Zuckerberg, when he was writing Facebook for the first time, thought that Facebook was going to be the behemoth that it is today, running on the number of servers that it's running on today, servicing the amount of requests that it's running today. You just can't fathom if you're building something at a Death Star scale, what you're going to have to worry about. And so you start by writing your application and working on your functionality. It's part of that loop I was talking about prototyping and developing your application. And hopefully you're thinking about enough of the right things to get it mostly right to begin with. But from an overall perspective, you just can't think about all those edge cases that you're going to run into. And so you don't start with blueprints for the Death Star in a startup. You don't have enough time to build the Death Star in a startup. You don't have a lot of time to think deeply about your application and what your applications are going to be, right? You want to be first to market, or you want to be noticed, you want to get your application out there quickly and get it in front of as many people. There's a drive for market share, and you need to grow your business. Before I can pay engineers to think really deeply about how I'm going to have an application stack that performs really well, I actually have to have some sort of model to pay for it. That may be DC, and I'm going to operate in stealth mode for a year, year and a half, 2 years, and hopefully nobody comes to the market before I do with the same product. Or you're bootstrapping and you're developing and prototyping and releasing quickly in an agile method. You want to make sure that you're engaging users, but at the same time, you want to make sure that you meet the spec of what the product is supposed to be, whether it's coming from a product development group or it's your own internal idea, right? Something you thought of. And you want to get it done yesterday, right? In a start-minded focus, waiting 6 months, 12 months, 24 months to get your product out because you want to worry about every edge case and scaling is not effective. You're going to spend 24 months working on trying to create the most scalable application architecture you can, and you're going to go to market, and users aren't going to like your product, and you spend 2 years and a lot of money, and you're not going to have an application you have to worry about scaling in the first place. My yearbook's Codebase history follows this model. When I inherited a Codebase in early 2007, it was monolithic. It was so monolithic, it was tied to the server that it was running on. Getting it to be off of the server that was running in production and running somewhere else was a task unto itself. Fixing hard-coded paths and dealing with hard-coded IP addresses within the software was just the tip of the iceberg. And in 2008, we set forth to use a loose services-oriented model, right? Traditional model, when you're reading enterprise service bus type of stuff, and you're looking at a service-oriented architecture, each thing is cyclic, and there's no interconnectivity. There's basically you're talking APIs across from each other, and there's a shared nothing architecture. We're loose on that. We share common databases, for example, for member data. We share common databases for the social graph, that sort of thing. But at the same time, it allows us to scale out applications in a way that we've done it to say that this particular one application needs 20 web servers, and we can scale those 20 web servers out without impacting the rest of the site. And if a particular service becomes slow, we need to turn a service off because there's a problem with the database server. We don't impact the rest of the site, right? If I have to turn off the casual game section of my yearbook, it doesn't impact the overall site engagement for anything but that particular piece. We have very loosely coupled architecture that allows us to think about these particular components, other than the core aspects of user data and that sort of thing, as individual resources. 2010 has been an important year for us because as we've scaled, we haven't had a lot of that time to think about in performance. Our solution for addressing scaling has been a combination of addressing scaling within trying to meet key metrics for page execution timings and by runtime. And we have a lot of hardware to meet the amount of performance and load that we have on the site. So that being said, avoiding unnecessary disruptions is key. And it's very easy as an engineer to say, ooh, shiny. Something new has come out, something that's going to help me scale better, something that is going to make my application perform better. And it's very valuable to go down some rabbit holes and look at that. It's very important to know what's going on and take the best of what applies to your domain and do so. But unnecessary disruptions can lead you to not be focused in what's important about developing your applications and scaling them well. Reengineering is one of those. If you look at some of the major issues that have happened with two large named sites within the last 30 to 60 days, Dig, Twitter, both have had major issues, different types of issues, but both issues stem from the concept of I'm not just going to revamp the product, I'm going to re-engineer the product. I'm going to throw out everything that was old, and I'm going to bring in the new best of breed. And it's a tendency that I understand as an engineer. I want to go and take the lessons that I've learned in 2010 and apply them to the things that I did in 2007. But the stuff I did in 2007, I don't want anybody to look at, right? And so in the case of Dig, one of their their biggest mistakes that they made was they, at the same time of doing engineering revamp, they did a product revamp, and so you get this combination of new product that users don't like, and you have engineering issues because you didn't account for every edge case that you're going to run into when you're swamped with all of your traffic. Twitter, introducing new security issues by changing their engineering model led to some pretty serious exploits. So re-engineering for re-engineering's sake is an unnecessary distraction. I'll give you an example out of my yearbook. Recently, we undertook a major project to revamp the way that our session system works and our login system works. It was a key business decision. It wasn't a distraction, an unnecessary re-engineering or re-engineering for re-engineering's sake. We actually had to set business goals for it. And it was a system that went through multiple months of development and at least a month of QA, worked great in our development sandboxes and our multiple stages of testing and staging and production as we peel off machines to test how it would behave in production. And then we rolled it up. This was a Thursday morning. And we started seeing users hitting redirect routes. And so we're like, well, why are they hitting these redirect routes? And so we jump into Splunk and we've instrumented pretty low, so we're watching these kinds and we're seeing these things happen. And now instead of having the small engineering team that was working on that particular piece, I have every one of my senior architects, I have every one of my senior developers, and we're all looking at the problem. Myself, my VP of engineering, my VP of NetOps, our database administration team, we have all now stopped what we were working on to look at what's going on inside of this particular one issue that we're seeing, that is redirected. And it's not all of our users. The site works fine for most people logging into the site. It was less than 1% of our issues. But it was less than 1% of our issues that escalated, that amplified our page views on site by something around 20 to 25% of additional load, because browsers are redirect moving and they're loading pages as quickly as they can. So by Thursday afternoon, we solved that issue. By Thursday night at 2 in the morning, we had solved about 10 issues and we still had 5 left. By Friday at 5 p.m., we had solved an additional 5 and found 8 more. By Monday, we figured out that Google released Chrome version 6 that has a bug within the analytics. And one problem that we spent all weekend trying to track down is actually a bug in Google Chrome. The point there is that we went and we re-engineered something that was core to the site. And it became a huge distraction. And in our case, we had a justifiable business need for it. But I guarantee you, if I didn't have a justifiable business need for it, the CEO would have been even less happy about what was going on than he was, right? And it reflects poorly on me as a technology leader within the organization if I'm just making these wholesale technology changes because this is a better way to do it. If it's working, it's keeping your site up and running, make sure that you focus on the important pieces. Decoupling processes. One of the things that we started to do in 2008 is we looked at page execution timing. I brought that phrase up a lot. We want to know from the point where a user request comes into the browser, the point where our application has finished that request, how long does that take and why does it take so long? And there are key things that happen, right? When a user starts a page, we're going to start the session data, we're going to grab user data about that user, there are common elements on the page that we're going to grab, do they have messages waiting, all the way down to the specific application logic for that page. And then they're going to take some sort of action, right? Let's say it's a simple email system, for example. I'm going to send an email. Is there really any reason why my web application actually has to construct the email, talk to my SMTP server, and send it out? Not really. Can I come up with a more effective way? Can I bundle the post data and send it down to a message bus and let it go through all the logic? And I say email, in our case, we have a lot of application logic around email. Is this user logged into the site? If so, then we need a site engagement email that gets them back to the site. Has the user received free emails today? If so, let's send another. Things like that. And so why spend the time in the application that's trying to be fast and talking to the user and checking all these business logic rules about sending email? And so what we did was we sent that message off into a message bus, and then we have a pool of consumers on the back end who's having to check that business logic. The user's gotten a fast response that says your message has been sent. We expect that it's going to be sent. And the back-end piece is now churning through all the pieces that are required. Doesn't this user even want to get email? Have they blocked email? All those rules before we send it off. And so it allows for faster page generation to offload those key pieces or operations that you would traditionally think of when you're prototyping your application as sitting within your application stack with that page execution and moving it somewhere else. It allows you also to take CPU-intensive tasks. The user uploads an image. If I really want my PHP app, my Python app, my Ruby app, whatever it is, to spend a lot of time for the user resizing that image into 6 different sizes or 3 different sizes that I need for my application to perform the way it's supposed to perform. Now, upload the image, stick it somewhere, send a message that says a new image has been uploaded, and let some sort of background process run and resize those images. That's CPU intensive. There's no reason to add that time processing images to my web applications here. And so now I can scale those particular tasks out on their own hardware without having to add to my web front end, which is key, because if you remember talking about Postgres and the number of connections that Postgres has, the slower it becomes. The same is true with other datas, right? If my message brokers have 80,000 connections into them, they're inherently not going to behave as well as if they have 10,000 connections to them. And so basically, we want to scale as little of our web tier as possible and push as much complicated logic where we can and it fits the application overall architecture and user experience. We want to push that off somewhere else to think about it. It allows us to throttle activity. So one of the things that I found early on in my yearbook, we have this pervasive virtual economy. We call it lunch money. And it drives user engagement. They're earning lunch money dollars. If they log in, they're earning lunch money dollars. If they're flirting with somebody, they're spending lunch money dollars. If they want to buy a photo or send a virtual gift, or they want to use it in some sort of game mechanic. And so what did that yield? That yielded smartish people who use our site started writing apps. And they were writing these apps in Visual Basic and Delphi and other Windows languages that would automate harvesting money on the site. They would automate adding friends. They would automate sending flirts and playing games. And so we saw this activity in it. And it's like having an API except for, well, it's not an API. I didn't design it to have somebody's app hitting the page 10,000 times for one user within a minute, right? And so by decoupling those activities, decoupling the sending of a flirt to somebody on the site, I can artificially throttle how quickly that user is doing it. And I'm also not tying up web server resources by hitting that page over and over again, checking the logic that says, this guy's spamming me, right? And then Theo talked about this yesterday. One of the great things about messaging is capping streams for other data. A good example of this is our comment system. Comment on a photo, you comment on an activity, a status post. But we use queues to send that comment down through the system into the database. But at the same time, we tap that same thing. We use it for behavioral analysis. Is this a Nigerian 409 scammer who's trying to trick this large pool of people into doing what they're doing? Is it inappropriate content? Is it somebody who is for example, we care a lot about age. It's one of the key things that we focus on in differentiating our applications. We don't want 13-year-olds talking to 20-year-olds. And we don't want 12-year-olds posing as 16-year-olds. And so we'll look at the message coming across, and if we see, I'm really 12 years old, we're going to take some sort of action, right? Because it's illegal to store that 12-year-old's data, even if they say that they're 16. And so our background processing systems are going to look at the messages and say, are there keywords being met here that cause us concern that we need to send this to our safety team to review? If I was doing that in my web front-end application, my application would be terribly slow. So we enqueue into ActiveMQ or RabbitMQ. ActiveMQ is a great product. We've been using it for a long time. We just find that there are some performance implications at our scale. It generally slows down over time, and We made a decision about a year ago to move to RabbitMQ and have been doing so in a steady manner going forward. And we developed a consumer framework for talking to RabbitMQ that is elastic. Within guidelines, it will expand automatically threads and processes to meet the demand of greater workload and then pull off consumers on the box when we notice that everything is within normal guidelines. It allows us to target our workloads. I think I mentioned each of those 3 use cases. Storage. We have a lot of user-generated content. Users uploading profile photos into our applications, and we only expect that this will actually accelerate quite quickly. I've seen a number of strategies employed at similar companies. We decided to go with a scale-out system early on, the Isilon scale-out nest, and I really like this product. I'm not in any way being asked by Isilon to make this pitch, but it's really cool. It's a FreeBSD box basically underneath the covers, and you pop it in, and you set up a cluster, and you need more disk space or more throughput, you pop another node on. And you need more, you pop another node on. And they just expand elastically like that. I can take them off, put them in. There's also redundancy across the nodes, so I have n plus whatever I want to set to for my node, so I can actually lose a node out of my cluster without using content. They automatically rebalance, all that sort of thing. It takes a lot of the management out of some of the other approaches that I've seen of having farms of boxes with JBOD or whatever storage attached to them and having to figure out individual servers that I'm going to target user content at. We use NFS, they have multiple protocols that they support. It's been one of those things where I've been able to put this up and then not have to worry about or think about how am I going to scale out my storage for user-generated content. Database servers. Boy, we've gone through a lot in trying to figure out what the right solution is for database servers. We obviously care a lot about our database servers. It's what keeps us running as a dynamic site. And so we've evaluated SAMs, we've evaluated Fusion IO cards, we've evaluated pretty much every major product you can think of from a storage perspective, and how are we going to use it within our data center. And we still keep coming back to direct attached storage. It's fast. It's easy to administer. And for a single purpose machine, not only is it cost effective, it's going to give us a solution that we can put in place, deal with replacing disks when they go bad, and move on. SAMs, I find, have a different performance focus. A lot of them are very enterprisey, and they want to deliver a certain amount of performance to as many nodes as they can. They're not going to be extremely fast for one node. They're going to be fast for 20 nodes. We don't care about that. We want the fastest I/O throughput that we can get for an individual box. And so we had a SAM early on and spent a lot of time, probably 6 months, trying to tune it, to work with the company, to work with every consulting company that we could find that had some experience in performance tuning with I/O. We talked to every major company about performance tuning, and we keep coming back to direct attached storage. And now with SSDs making their way into direct attached storage, I don't have a compelling reason to go to a type of SAN or NAS for our database. And besides all that management overhead, the SAN overhead, all the different things that go into that, they're expensive. I spend a lot of time managing it. NetApp, having a guy who knows NetApp and can focus on managing my NetApp is more expensive than having a guy that knows how NAS works and can swap drives out and be an operator. Got about 5 minutes or get that, so I'm going to breeze through these. Managing vendors. Part of our scaling success has been making sure that we have good relationships with our vendors. And not all vendors are created equal, right? CDN, we've been through 4 or 5 different CDNs. And we found that moving off of one particular CDN, and I'm not going to name the name, to another, increased our overall page view activity by a pretty significant number. It decreased the latency, and it goes to that whole thing that everybody's talking about, speeding up page delivery, increases engagement. And so we were very pleased, and then we were kicking ourselves for saying, why did we spend a year with these guys and not evaluate anybody else? Hardware support by vendors, it differs. Vendor X versus vendor Y. We spent a lot of money in 2008 with one particular vendor, and I ditched them in 2009 because their support sucked. Their support sucked so much, this went down on a server once, and they said, reboot the server. I'm like, you don't understand, this is a production database server, and it's a bad disk, and I just want you to send me out a replacement disk. Well, our first step is you have to reboot the server. Before we're going to talk to you about anything about the device, it may clear up any problems, so reboot your server. No. It doesn't work like that. And so they lost a multi-million-dollar contract because they wanted us to reboot servers when disks went bad. And then they spent all of 2009 saying, hey, come back to us, please. Come on, fly down. We'll let you meet with the CEO. We'll get you a special support system where you don't have to reboot the server for disks. Like, you don't get it, right? And communication is key, and fostering good relationships is key. When we were heavily in the SANs and going down that road, or even the ISO and stuff, hardware fails, right? Just like Brian said, when you've got 5,000 disks are going to fail. When you're driving to the data center in the middle of the night because hardware failed, being able to get your sales rep on the phone or your primary point of contact on the phone and say, hey, buddy, please help me out here. It makes a big difference than calling the support line. And having that relationship is really important because they're going to push from another direction to make sure your problem gets resolved as quickly as possible. Extra effort on your part generally yields extra effort on their part. Right? Keeping a good relationship, Message Systems is a great example. We had a problem with Momentum when we upgraded, and I like to think we have a good relationship with them, and I called them up and I said, hey, we're having this problem. Can you help us out? And within a very short period of time, all people were on deck, and we had people in our office trying to help us resolve the problem. And lastly, I talked a lot about technology and things that we have, but focusing on your team is as important as focusing on tech. People are not expendable, and in a startup environment that's fast-paced and growth, you need people to do the extra effort. You need to make sure you're not treating your coworkers or your employees as just programmers who are coming in. One of the things that we like to do is take some time aside, at least once a year, where we get you guys out of the office for a couple of days, and we talk about big picture items, we talk about small picture items, and we play dodgeball. And it makes a really big difference in thinking about how we engineer at scale when you take time and you step back and you look at the big picture and you're not focused on your monitor all the time when dealing with these things. And so that's it. I don't have a lot of time for questions. I'm happy to answer any as quickly as I can or outside of the room. Please follow me on Twitter if you find any of this interesting and want to see what I'm doing. That's my blog. So if there are any questions you think could be addressed by the group or from groups, happy to take them. Yes?
When you have your consumers doing the back-end work, do you like to shed machines to particular tasks that you mix them, which are expanding dynamically, multiple things like manufacturing?
Yes, I generally have certain groups of machines that are dedicated to specific tasks. Just for that exact reason. Also, it makes it a lot easier when we get a page at 2 in the morning that says this particular queue is backed up beyond what it should be, knowing exactly where to find the consumers that are running and run one interactively and figure out what's going on is a lot easier. All right, yes?
What do you do for configuration management?
We have an in-house system that we built that lives on top of a persistent memcached backend that we actually use that multi-tiered caching approach I talked about where configuration data gets pushed out into memcache basically, and when we pull in, then they cache based upon what the configuration data is for predetermined around time and machine-specific shared memory pooling. And then we also, it really depends on the type of configuration as well. For general machine deployment type of configuration, basically we keep our configurations in some version. And on Bootstrap, kickstart the machine and boot up, then go pull that configuration down from some version and push it in. And then we have scripts that basically go out and push, like Topper Chef type of stuff, that go out and push those configuration fields.
If I understood correctly, you said your primary database, when that fails, you have to use a switch.
Yes.
So, this is the manual operation.
It is.
So did you try to automate changes?
We did. There's generally a human judgment call that has to take place that says, am I having a problem with this database because of something like a out-of-control query? Using HA and RB and looking at, did my machine go down, that's an easy decision, right? But generally, what we're looking at is something weird going on, or did I have some sort of corruption because of this subsystem machine? And what I generally like to have happen is a DBA come on the machine and say, hey, wow, there's this out-of-control query that basically locks out, to a large degree, and I'm going to kill all that off. I'm not going to swap over to the machine. So, there's a judgment call on all that. We have looked at HA, we do use Heartbeat for some stuff, but for Postgres in general, we like to get the hands-on analysis prior to switching hardware because there's a significant amount of investment of manpower involved in that. Setting up form standby, warming the database, copying everything over, work. Yes.
Here's your
We have a very large code base, and right now our subversion repository is everything, one repository. I can split all that up, but we're trying to move to a model where our code base is more micro-focused on either services or other applications. And from the Git approach, everything from to check out the application and pull it onto my local machine and do all the work, keep all my commits and push it on Monday. Just the distributed nature of Git, the way that it works, fits our development model better than having that one subverting repository that I'm going to get all my code in the PDM. Not currently. Currently, because of the fact that we're locked into this subversion, and when we're locked into subversion, we have an array of boxes. Thanks.